Hello, in this tutorial video, I'm going to show you how to build iron-carbon diagrams using the Isopleth function in JMatPro. For this, we are going to use a chemistry extracted from the ASTM A29 standard for a steel alloy. In this window, I have the ASTM A29 standard, which basically specify the different compositions and limits of compositions for steel bars or carbon and alloy hot rod products. So we are going to select from those tables a particular composition that we want to model, and particularly to design the iron-carbon diagram for this alloy. In this case, let's select, for example, this manganese steel, which is the grade designation is 1541. So I'm going to select that one. And notice that there is a carbon content between 0.36 to 0.44. For the case of JMatPro, I'm going to select carbon 0.4, kind of in the middle average. Manganese, in this case, is going to be in the order of 1.35 to, notice here, is 1.35 to 165. So I'm going to select in the middle, let's say 1.5. Phosphorus and sulfur are just specified maximum. In this case, 400 maximum ppm and 500 maximum sulfur ppm. Those are really high values for current practices. So let's say assume that phosphorus is 0.01 or 100 ppm and sulfur 100 ppm as well. Additionally, we should put some nitrogen in our simulation because that's gonna, most likely this material is gonna contain some manganese sulfide. It could produce some nitrites. So in this case, depending on the cleanness of the steel, we could have 50 or 100 ppm of nitrogen. Let's put 50, so it's 0.005 ppm of nitrogen. And basically, that's what we need for our simulation. Now, there are some remnants or incidentals in the steel that usually we need to consider. In this table, this standard doesn't give us any incidentals for manganese steels. But if we go to the table number 2, here in the note number 1, it's saying that there is some maximum incidentals that can come in the steel, including copper, nickel, chromium, and moly. That's because, you know, the steel can get affected by like the charged material that was used, including like some scrap or another, you know, compositions that were cast before. In this case, those are high alloy steel, so we are not going to use any of them. But we need to consider silicon. Silicon is usually very common to use. Now, exploring the table number 3 is telling me the different limits or ranges that are acceptable, lowest limit for a particular composition. For example, silicon, the lowest limit is 0.1, means that some of the incidentals of silicon could be 0.1. So I'm just going to add 0.1 of silicon in my composition there, because I'm probably going to be an incident. Now, to build the iron-carbon diagram, I'm going to use this function called Isopleth. And I need to select the different options here. In this case, the valence is going to be iron, and the element that I'm going to vary is carbon, because I'm going to do an iron-carbon diagram. I'm going to just simulate between 0 and, let's say, let's say 0.1, and in intervals of 0.01. That's the simulation that I'm going to do. And the temperatures are going to be from 1600 to 600 in, let's say, in range of 10. So every 10 steps on 10. And so that's the simulation, and we are going to consider different phases that are forming there. So now we're going to run, and we'll be back when we have some results. Now, this is the result that we obtained from our simulation. I'm going to make it a little bigger here. And here we have our composition. That is the Isopleth. So we have composition from 0 to 1 carbon in 0.01 simulation. And the temperature was from 600 to 1600. And so you'll start to see different phases, starting from liquid. We have some delta ferrite, austenite, and the ferrite in the lower temperatures. But when we increase the carbon, you'll start to see that the austenite expands. And also we have some phases that are forming, for example, the manganese sulfide there, because we added some sulfur. So manganese sulfide started to form high in these temperatures here. we'll see that the different points have moved a little bit. So this is the peritectic point of the diagram at the top, and this is going to be our eutectoid point of the diagram. We can also select something, search mode, very interesting feature here, where we can just highlight a particular phase that we are interested. Let's say that we just wanted to see where the manganese sulfide is present. So we can say where the manganese sulfide is present and the ferrite present, for example. So it's just here and here. In the other areas, there is another phases. So that's a pretty easy tool to see, where the phases are located. Sometimes the diagram is too busy, so it's hard to see. So that's a easy and a nice way to reproduce a diagram in JMatPro. Finally, here I'm comparing the diagram that we created in JMatPro for the 1545 steel, which is a manganese steel with, couple of incidentals there, including sulfur, nitrogen, phosphorus, and silicon. We added silicon as well. And this is just a plain iron carbon diagram that I also plotted in thermocalc. So if you want to see how to plot this in thermocalc, I have another video in my channel where I explain how to do this kind of diagram. But in this case, I just plotted here to compare the plain carbon, iron carbon without any alloy elements with the one that we created by JMatPro using other elements. It's important to say here that I also can do the same in thermocalc, but sometimes those calculations are longer, are more slower in thermocalc. So you need to be careful with the number of elements that you are in thermocalc, because that could take a lot of time to solve. JMatPro usually use like some empirical models that solve much easier, but it gives a decent result. So notice here that I'm having the same ranges from 0 to 1, from 600 to 1600. This case a little higher, but 1600 is here. So we have similar phases. In this case, the peritectic point is pretty clear, between the delta ferrite and austenite here. In here, it's not that clear because we have this new phase that forms, which is the manganese sulfide. So it's basically divided in different subregions, but we have the peritectic region there. Now, the interesting part is related to the eutectoid point. We know that in the carbon diagram, the eutectoid point is located, in this case, approximately at 0.77 and 714, approximately, there's 720, the temperature. But in this case, the temperature seems similar in our alloy, but notice that our eutectoid point have moved to the left when we increase the manganese and the incidentals in our alloy. So it's closer to 0.7, so have moved to the left. It means that the alloy elements are affecting the eutectoid point. So that's interesting to notice. And also you can notice, that using the full composition of the steel, we can see more kind of detailed phases, including the sulfides regions and a couple of details that are not shown in the plain carbon diagram. So I hope that you find this tutorial useful. We just went to JMatPro to use the Isopleth option and built iron carbon diagrams with a actual steel composition.